Welcome back. This is an Aleks training video on counting sigma and pi bonds in a small molecule. A sigma bond is a straight end-to-end sharing of electrons. So if you were to have two, say S subshells, and they're sharing a region here, so like two hydrogens, each with one electron in it, and they're sharing together, you'll end up with an H2. All hydrogen gas is H2 because it's so reactive. They want two, they don't want one, and so they'll share. If you were to have two P, let's say this is an X subshell for a P, and here's an X subshell for a P, and it's an end-to-end sharing, that's also a sigma. Okay, so a sigma bond is a single bond. A single bond. If you were to have, let me show you a picture. So let's move here. Okay. So I've got two atoms here with not just a s orbital in the middle, but also y orbitals. This is a y sub or a p, or remember you have s subshells, p subshells. P subshells has three. There's an x-axis, a y-axis, and a z-axis. So these y-axes are sticking up above the plane of the molecule. If they share a region of space that is sharing an electron between them, that is called a pi bond. And a pi bond is more than just a single bond. You would have a pi bond in a multiple bond, like a double bond or a triple bond. Take a look at this for a second. If I have these two, this is a carbon with a hydrogen group attached, and it's going to attach to another carbon. Okay, so what you're going to get is one of these subshells, these X subshells, will overlap, and that's a sigma bond, just like a normal single bond. But you're also going to have a sharing of these guys, top and bottom. That would be a double bond. And then you're going to have a sharing of the front guys, front and back. That's a triple bond. So a multiple bond is going to be a sigma plus a pi, that would be a double bond, or a sigma plus two pi's, that would be a triple bond. Okay, so if you have a single bond, it'll be only a sigma. Okay, if it's a double bond, then you're going to have a sigma and a pi. If you're going to have a triple bond, it's a sigma and two pi's. Okay, so we now need to talk about hybrid molecules or hybrid orbitals. So a hybrid orbital, in reality, in order to explain properly what you see when you see a bond or a combination or how molecules are actually shaped, the current theory that makes sense, that's answering all the questions right, is kind of wacky. I thought it was wacky first time I learned it. I think you'll find it wacky. But what's actually happening in reality, I suppose, is that the electron, say, is in an S subshell. Let's say that's the 2s. And normally a 2s, there's going to be 1 and 1, 2s. And let's say you have carbon. Here's the P. Carbon is going to have 2p2. Well, energetically or energy-wise, it would actually be preferable to get rid of that electron and give it its own room, just so that this P subshell is nice and spread out. That's kind of where what's really going to happen. Okay, it's like if you're at a rock concert and there's 5 seats together on the third row and nobody's there, and it's the second half and no one's ever gone there. You probably can go from the nosebleed section down there right in front of the stage and stand there because it's available. That's really what's really going to happen. Just because that these electrons have spaces that they're supposed to stay in doesn't mean they're going to. They're going to go wherever the energy's good. Okay? So what this is no longer an S and a P, because the S isn't full and the P is now fuller than it should be. So this is hybridized, and this is going to be called an sp3 orbital. All right. If you were to have a 1s and 1p, and it hybridizes, you're going to get an sp orbital, which is linear. Okay, linear, remember, a straight line shape. If you have a 1s and 2 p's, it'll hybridize to an sp2, which is triagonal planar. Okay, so you're going to get the 120 degrees straight, like it'll be just on the same plane, as far away from each other as it can. If you have, in the case of carbon here, we had 1, 2, 3, 4 electron domains. So you're going to have 1s and 3p. You're going to get an sp3 orbital, and it's going to be a tetrahedral shape. All right, so between these two pieces of information, you should be able to answer the question. First question says, how many sigma bonds does the highlighted atom participate? Remember, sigma bonds is single bonds, overlap. So I've got one single bond here, another here, another here, another here. So I have got 4 sigma bonds. Okay. How many pi bonds does the highlighted atom participate? Well, there's no double bonds here. There's no triple bonds here. So there's 0 pi bonds. Pi bonds is only for multiples. And then what is the orbital hybridization of the highlighted atom? Well, how many electron groups do I have touching the carbon? Okay, I've got 1, 2, 3, 4. Okay, that means I've got 4. 1 plus 3 is 4. So it's going to be an sp3 hybridized orbital. I would call this hard. I would call this hard. I would call this hard. This is something that you're going to have to ask a million questions, write it down, do practice, and it will eventually dawn on you what's going on here shape-wise, energy-wise. But I promise I'll try to explain as best I can in class.